Now we will go for rectangular microstrip antenna design. In this, we will understand the design technique and we will go for the we will do one design of the antenna. One design also we will do. So we'll see that how it can be designed. There are two methods, cavity method and transmission line model method for the analysis. So the transmission line model is popular and it is used. So we will discuss based on the transmission line model method. Okay. So this is what the method of analysis, how it can be designed, and starting with the rectangular microstrip antenna. So compared to the transmission line model, the cavity model is more accurate, but at same time it is more complex. So as I told that there are two methods. One is the cavity model method and another is the uh, transmission line model. So transmission line model is the approximation. It is considered as the antenna as a transmission line. Okay. Microstrip antenna. Mainly this method is for the microstrip antenna. So it is taken as antenna as a transmission line and then the analysis is done. Then you can design the antenna. Cavity model is somewhat complex and complicated, and based on that the you can do it is more accurate, but it is somewhat complex. So for the basic understanding, the transmission line model is preferred. Rectangular patch antenna is most widely used configuration. So it is a very popular, easy to understand, easy to fabricate. So rectangular patch is the basic, you can say the basic type of the microstrip antenna, and that we are going to design here. Okay. So now transmission line model. So we are considering this as the transmission. So this is the microstrip line, and microstrip line means it is actually the what your antenna. Now the transmission line, microstrip line is having, this is what the width of the line and this is what the length of the line. Same terminology we have used in the antenna. So transmission line had a more larger length, but microstrip antenna has a limited length. That is only the difference. So that we can estimate. H is the height, epsilon r is the substrate, and this is what the side view, this is what the top view. Okay, this is what the you can say epsilon effective. Now, what is this diagram and how we can correlate with this? Now, this is electric field. Now, how electric fields will be radiating? Now, you can see this is the upper patch and this is the ground plane. Electric field, they are starting from the upper patch and terminating at the ground. Okay, this is analysis, how we will analyze. Now, if you will see here, the sum of the radiations, that is the electric field, they are in a space, that is in the air, and some portion that is in the substrate. This is what the substrate. If you will see, it is radiation is this way, and here it is shown as a bend, and then it is going. So everywhere some little bit bend is shown. So it is intentional, it is not the mistake. So it is intentional because as the epsilon of the air is 1 and the epsilon of this dielectric, that is relative epsilon r, is something else, that is 2.2 to 12 something. So there is a bending this way. Now whatever the epsilon of this material substrate you have taken, but the radiations are from the air and some are from this. So we have to calculate the effective epsilon, means whatever this epsilon is not the actual epsilon for the radiation. So we have to calculate the effective so that we can actually consider the resonance frequency, at which frequency it will resonate. Okay. So, so here the effective dielectric constant, that is epsilon, is dielectric constant of a uniform direct material, so that the line has the identical electrical characteristics. Okay. Now you can see here whatever for electric field, W by H ratio if it is greater than 1. What is W by H? This is W, that is the width of this transmission. And this is what H. So if W by H, if you will take W by H ratio, if it is more than 1, generally this happens, W by H ratio. So width is higher than the height. Okay. So if this is the condition, the effective epsilon is taken by this model. So what you are taking here, so epsilon R plus 1. From where this 1 came? Epsilon R is the epsilon value of dielectric value of this substrate. And what is 1? 1 is the relative permittivity, that is epsilon R of air. So directly it is taken 1. So it is epsilon R plus 1 by 2. So it is taken 50% of this and 50% of this. Okay. Then epsilon R minus 1 by 2. Epsilon R minus 1 by 2 into 1 plus 12 times H by W to the power minus 1 by 2 means under root of this. So by this formula, you have to remember this formula. By this formula, we can calculate the effective epsilon value, that is effective dielectric constant of the substrate or the antenna, epsilon. So very first in any problem, you have to calculate this first. Okay, effective. And this is what, why this is so? Because the radiations are from the air and some radiations are from the substrate. So that's why this formula. This is simple. Epsilon R plus 1 by 2, epsilon R minus 1 by 2 into 1 plus 12 H by W. It is the ratio of H and W. So it is H by W. Yes, it is combination of substrate and air because the radiation is from the air and from the substrate. So that's why it is taken as a combination. And obviously the width, because if you will have a more width of this antenna, so if this is the width, so if it is extended more, suppose I'll just show. Actually, this width is shown here, and if this width is extended, suppose till this, okay, so more radiations are from outside this way. Okay, so that's why it is width dependent. So that's why it is taken width W by H. And if your height is very large, okay, so again more radiations will go through the this. So that's why this W by H ratio is taken. Okay, understood. So this is what the reason here. Due to this reason, these parameters are taken. So these are okay. Question is, sir, if antenna is used in water, then water will also come into picture. Yes, generally water, you can say the sonar, but the main in the sonar, water generally we don't use the electromagnetic antennas. Sonar is the one of the application directly come in my mind. That is that is the submarine. In submarine, they are using the ultrasonic waves, so not the radiating the RF waves. So in the water, RF waves are not that much effective. In air, they are effective, so they are not used in the water. Okay. So this is what the effective dielectric constant. So this is the formula you have to use. Now, what is this diagram? So this diagram I have taken, that is for low frequency and for the high frequency. This is what called the empirical result. Empirical result means based on the analysis, based on the design and the experimental result, they have drawn some graph. So these graphs are called the empirical result. This is what effective electric constant, dielectric constant. This is for your understanding. This is effective dielectric constant, and this is what the frequency. Now, effective dielectric constant is also frequency dependent. So generally for the lower frequency, it is remaining constant, but for the other frequency. Now, if you are calculating effective dielectric constant as 2, then your epsilon r is 2.33. Means obviously, whatever your epsilon r, it is more than 1. So your effective will be always less than 1. For such frequency, it is for, if you will take for this example, so it is almost constant for frequency from here. I think it is gigahertz, 9 to 13 gigahertz. It is almost constant, little bit variation. But if you will go for the higher dielectric constant, the effective value is changing. And if you will go for more, that is more than 10.2, so the effective value is changing. So generally, if you will take the lower dielectric constant, so it is remain generally the constant for the range of frequency. But if you are going for the higher, so it will be for the it will change accordingly, and this width and height is taken accordingly. This is the specific, this is what called the empirical result. Means this is tested for this width of antenna is this one 0.3175 centimeter, and height of antenna is 0.1270 centimeter. And these are the different. This is for your understanding that how the impact is there. Then transmission line model. Now one parameter, now 2-3 parameter we are going to calculate. So effective effective dielectric constant we have calculated by this formula. You just remember this formula. Then transmission line model, again we will go for the effective length in this. So whatever the length is, how much is the length? Now as this is what the patch, and you are taking this as the length. Now you just see the radiations are outside this length also. Means actually the length of antenna is this much, but the effective length is additional, that is delta L from this side and delta L from this side. So the length is not simply L, it is more than L. Here, whatever the effective dielectric constant is less than what it is actually, but the length, it is more than that what it is actually. So again we have to calculate the effective length. So this is what the formula, that is delta L by H. So we have to find it out how much is the delta L, how much radiations will be there. It depends again on the width, height, and effective epsilon. Okay, so these are the parameters. So delta L by H is given by this formula, that is point. Again, this comes from the empirical result, means they do the analysis and then they develop this formula. So lambda by H equals to 0.412, effective epsilon plus 0.3, W by H plus 0.264 upon effective epsilon minus 0.258, W by H plus 0.8. You have to remember this formula. So whatever the effective length is L plus 2 times of delta L. So delta L you will get from here. You will have the value of H. Effective epsilon just now you have calculated. W is given in the formula. H is maybe also given in the formula. So you just put all these value, you will get the delta L. Effective L, you will get L plus 2 times of delta L, because it is on the both the side. So you have to add 2 times. Okay. So this is what the transmission line model. Now we will go for the problem. So only 2 parameters you have to calculate, length as well as effective this epsilon L. Now how? Design procedure. This is what somewhat interesting. Now we are going for taking one simple problem for the rectangular microstrip antenna. So for the effective radiation, so you have to calculate a width. Okay. So W for this is what free space velocity is V. So for the efficient radiation, particular width that lead to good radiation is given by this formula. So this is what width can be taken 1 by 2 FR. FR is resonance frequency, which resonance frequency you need. So you can take this and under root mu 0 epsilon 0. So this mu 0 epsilon 0 you can take 2 by epsilon r plus 1. So whatever the dielectric material you are taken by this. So it is V0 by 2 FR under root 2 by epsilon r plus 1. So based on this, you can calculate the W. So for which, as you will change, V0 is your C, that is 2 into 10 to the power 8 meter per second. Epsilon r is material which you are selecting 2.2 to 12, whatever the material you select. If you will change the frequency, your width will change. So you can say your width is inversely proportional to your frequency. If you will increase the frequency, width is going to reduce. This is the very first parameter. Then second is determine the effective dielectric constant of the microstrip antenna, as we have discussed just now. Then once W is found, W you can calculate, determine the delta L. Just now how delta L can be calculated, that also we have find it out. So the actual length, now delta L is calculated. So rearrange the previous formula. So L plus delta L is equals to this, or you can say L equals to 1 upon this minus 2 times of delta L. So you will get the physical length of that. So you got physical length, you got the width, you got effective epsilon. So this is what the procedure. So we will go and solve why velocity of light is used in the formula, because the radiation is in the air, and it is found that whatever the electromagnetic wave radiate, they are radiating by the speed of light in the free space. Okay, the electromagnetic Poynting theorem what says, this is what electric field, magnetic field, this is direction of propagation. Now it radiate in the space. What is the velocity? So velocity is equal to the velocity of light or the electromagnetic field. Okay, so that's why speed of light is taken. So do you got this? Okay, so now we will go for the solving one numerical, very simple numerical. So this is what the numerical here. Design a rectangular microstrip antenna using a substrate. RT Duroid is the name of substrate. RT Duroid 5880. So this is somewhat specific, with a dielectric constant of 2.2. So dielectric constant is given. Height is given. Height equals to 0.1588 centimeter. Now you have to just convert it into the meter, whatever the centimeter, millimeter, whatever the things are given, inches. So you have to convert it to the SI unit, so as to resonate at 10 gigahertz. This is 10. Okay, so you have to design an antenna which will resonate at 10 gigahertz frequency. Dielectric constant is given. Dielectric constant is 2.2 and height is 0.1588. So we will start. So how to start? Starting from W. So what is formula for W? So 1 upon 2 FR mu 0 epsilon 0 2 upon epsilon r plus 1. So this is what you can rearrange this V0 upon 2 FR. You can use this. This is simple. So V0 upon 2 FR under root 2 by epsilon r plus 1. So give me the value of simple 3 into 10 to the power 8. Frequency is given, that is 10 gigahertz. Epsilon r is given, that is 2.2. You put the value and you will get the answer. This is simple calculation. Put the values in formula. So do the calculation, give me the value. How much you are getting? So this is what you put. This is 30, 3 into 10 to the power 8 and 2 into 10. So 30, why 30? Because 10 into 10 to the power 9. So this is what the upper part that has been cancelled, 2 upon 2.2 plus 1, and accordingly it will be in, you will get answer in meter, you can convert into the centimeter. Okay, so this is what W. Anybody got this answer? Is it correct? Just confirm if you got. If you will not do the calculation, you will not have the practice. So practice is important here. Then W by H is greater than 1. Yes, is it? Okay, it is correct. So now we will go for W by H. So W by H, W how much you got? That is 1.186. H is how much? it is 0.15. So W by H ratio, obviously it is more than 1. It is great more than 1. So we can use this formula. So this epsilon, effective epsilon, you have to calculate. So effective epsilon is epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 into bracket 1 plus 12 H by W under root. Okay. So this is what, if you will put the value 2.2 plus 1 by 2, 2.2 minus 1 by 2, because 2.2 is given here, and 112, H is how much? H is given here, that is 0.1588 by W. So both are in centimeters, so you can take directly, because this is the ratio, otherwise you have to convert it into the meter. So as it is simple one times, so as here it is taken. So the answer you got 1.972. So you just see here, that is 2.2 is your epsilon, and your effective epsilon is always less than 2, whatever is given, 2.2. If it is 2.2, it will be less than 2.2. So it is 1.972. So that means your correct answer. Anybody got this answer? So this is epsilon we did. Now what is the next? Next we have to do the delta L. Okay. So this is the formula delta L by H. So delta L by H, by this formula you put the effective epsilon. Now effective epsilon just now you are calculating. So you will get the H is there, effective epsilon is there, W is there, H is there. All these value you put. Just now I have put up here. You put and you will get the delta L. That is 0.081 centimeter. So you just put the L. So L you will get. So L equals to this is lambda by 2 minus 2 times of delta L. So this way you will get L equals to this, and you put this value here L. So you will get this, in this formula you will get this L. So all these value you have calculated. So this is what the simple numerical. So finally the effective length is L effective, you have calculated. So L effective equals to L plus 2 times of delta L. So this is approximately lambda by 2. Okay, so this much is the length you are getting. So this is what the simple numerical we have solved here. So this is for the rectangular microstrip antenna. And one simple problem, I'll go for the circular microstrip antenna. I'll need 5-6 minutes more. So we'll finish this chapter. Circular microstrip design. So it has only one parameter. So in the design of antenna, only radiations can be varied. Radius can be varied. So only one parameter here. No width, no length, only one, that is the radius. And analysis is done by the cavity model. So here the cavity model analysis is done. So we will not go into much analysis. I'll directly go for the numerical and the design. So here this is H must be here it is given. So A is what your radius. So radius is calculated by this F upon this. H is given. F is this. Okay, F is, that is this much, that is FR, your frequency of resonance, and epsilon R. So this is what calculated by the cavity model. So here H is there, again here epsilon, and this sorry. So here F is there. So here in formula there are two formulas. You have to remember this F formula. Calculate the F and put the F in here. So F is 1, 2, 3 times you have to put the F. F is one of the function. Okay. So this is the simple numerical we have to calculate only. Design a circular microstrip antenna for a substrate. Again, RT derive is given with a dielectric constant 2.2. Height is given 0.1588 centimeter. So as to resonate at 10 gigahertz. So to resonate at 10 gigahertz frequency. So this is what the dimension, and you have to calculate it. Yes, the formula, it is difficult to remember, but if you will put your formula on your desk and every day, morning, evening, if you will remember it, so if you'll see it and remember, so it will be easy, because this comes as a learning part, remembrance part. It is there. So formula will not be provided in your exam. You have to remember it. So various techniques are there, so that we can discuss later on. So F we have to calculate as the formula is given. So frequency is given, epsilon r is given. So F is calculated. So once you remember the formula, you have to put and calculate. Nothing is great. So this is what F you have calculated, and whatever the radius, that is, you put these values in this formula, and you will get the radius. That's it. So only radius calculation. It is very short problem, very simple problem. You have to calculate only the radius. Once the radius is calculated, everything, because h is given, epsilon is given, so only you have to calculate radius of the patch. That's it. The problem is solved here. So it is one step solution. Only you have to remember this formula. That is formula for the radius and formula for the f. That's it. So this is everything about the microstrip antenna. If you have any doubt, you can ask right now. Otherwise, we'll stop here. Okay, so we will just stop here.